Good morning, students. In this, we will study about wave propagation part 2. At the end of session, you are able to fundamentals of critical frequency, maximum usual frequency, and virtual height. Previously, we have seen that ionospheric wave propagation. Ionospheric wave propagation or skywave propagation is nothing but transmitting of EM waves from transmitter to the receiver over long distance. It is also called as point-to-point communication. The skywave propagation is carried out in ionospheric region. From the transmitter to the wave, transmitter to the receiver, the wave traveled in a vertical path and reflected from the ionosphere and reaches to the receiver. Okay, so in this part, the wave travel from transmitter to receiver through the reflection of ionosphere from over the long distances. That's why it is called as point-to-point communication. And the frequency range of skywave propagation is 2 megahertz to the 3 to 30 megahertz. That we all know that. So while traveling the wave in the ionosphere, the wave will take reflection from one medium to the another. While it travel from one medium to the another medium, it will take reflection. So while it reaching to the uh, Earth surface or nothing but receiver, they have some parameter that affecting the wave propagation. Now we will see some of that parameters and the frequency. They are called as frequency selection conditions. First, we will see the critical frequency. The critical frequency F is an important figure that gives an indication of the state of the ionosphere and the resulting high frequency wave propagation. It is obtained by sending a signal pulse directly upwards, nothing but vertical incidence. Critical frequency is defined as the maximum frequency at which the total internal reflection takes place in the ionosphere. The mathematical expression for critical frequency is given as Fc is equal to 9 root n max. Fc is nothing but the critical frequency expressed in terms of edges, and max is the maximum electron density or ionic density in the ionospheric region. It is expressed in terms of electrons per cubic meter. The critical frequency varies depending upon atmospheric conditions, time of the day, and the angle of incidence of the radio waves by the antenna. Next, next one is maximum usable frequency. It is also called as MUF. When a signal is transmitted using high frequency propagation over a given path, there is a maximum frequency that can be used. A maximum frequency that can be used for communications between two given locations. This frequency is known as maximum usable frequency. The maximum frequency that can be used for communication between two given locations. The frequency is known as maximum usable frequency. Waves at frequencies above maximum usable frequency are normal refracted. So slowly that they return to the earth beyond the desired location or pass on through the ionosphere and are lost. However, the use of established maximum usable frequency certainly does not guarantee successful communication between the transmitting site and the receiving site. The variations in the ionosphere may occur at any time and consequently raise or lower the predetermined MUF. That means the MUF is not constant. It will depending upon the variations in the ionosphere. The mathematical expression for MUF is given as Fmuff in terms of critical frequency. Fc is equal to Fmuff by secant theta, or Fmuff is equal to Fc by cos theta, where Fc is the critical frequency expressed in hertz, Fmuff is the maximum usable frequency, theta is the angle of incidence. The factor secant theta is called the MUF factor, and it is the function of path length if the higher layer is known. Next, lowest usable frequency. As there is a maximum operating frequency that can be used for communication between the 2 points, there is also a minimum operating frequency. This is known as the LUF, lowest usable frequency. As the frequency of radio waves is lowered, the rate of refraction increases. So the wave whose frequency is below the established LUF is refracted back to the earth at a shorter distance than the desired. The LUF is defined as the frequency at below which the signal falls below the minimum strength required for satisfactory reception. The luff is the practical limit below which the communication cannot be maintained between the two particular radio communication stations, nothing but transmitting and receiver. Optimum working frequency. Neither the muff nor the luff is the practical operating frequency. When the radio waves at LUF can be reflected back to the earth at the desired location, the signal to noise ratio is still much lower than the higher frequency, and the probability of multipath propagation is much greater. Operating at or near the muff can result in frequent signal fading and dropouts when ionospheric variations alter the length of the transmission path. The most practical operating frequency is one that you can rely on with the least amount of problems. It should be high enough to avoid the problems of multipath absorption and noise encountered at the lower frequencies, but not so high as to result in the adverse effect of rapid changes in the ionosphere. A frequency that meets the above criteria has been established and is known as the optimum working frequency. It is indicated as OWF. The frequency which is being mostly used for practical transmission and which has been predicted to be used over a particular period of time over a path is termed as OWF. Estimates the maximum frequency that must be used for given critical frequency and incident angle. It is the frequency chosen to avoid the irregularities of the atmosphere. OWF is given as 0.85 fmf or 0.85 fc by cos theta. Next concept is virtual height. When the wave is refracted, it bends down gradually, but not sharply. However, the path of incident wave and reflected wave are in same if it is reflected from the surface located at a greater height of the earth. Such a greater height is termed as virtual height. In the diagram, just see that from the transmitting end, the wave incident into the ionosphere. In the ionosphere, the wave taken reflection and it bent back to the uh, earth surface and reached to the receiver. In this one, the path is bending path. It is a bending path, curved path. It is a curved path, and the waves are extended. Okay, and this is the projected path. This is the projected path. This is the projected path, and it is known as virtual height. So this is the bending path is the actual height, and the projected path produces the virtual height. So this is the difference between the actual height and the virtual height. The bending path for the actual path produces the actual height, and the projected path in the ionospheric layer produces the virtual height. As shown in figure, the curved path reaches as an altitude of h1 before being returned to the earth. If the incident and return rays are extra plotted to a vertex, nothing but projected to meet at a vertex, they meet at a height of h, which is called the virtual reflection height of the ionospheric layer. So this is the bending path. This height is represented with the h1, which is a true reflection height, to produce the virtual reflection height, which is which is obtained by the projection of the wave into the ionosphere. Okay, what is the use of this projection? What is the use of this virtual height? The use of this virtual height is to find the distance between the transmitting and receiving antenna. Next, we will move to the skip distance or sky zone. The skip distance is distance over the Earth's surface between the two points where a radio signal is transmitted and at the point where it is received, having traveled to the ionosphere and been reflected back to the ionosphere. So not all the waves will reflected back to the ionosphere from the transmitted waves. Only some waves are reflected back which follow the required criteria. So the minimum wave, the first wave that reaches to the receiver through the ionospheric region, the distance is known as skip distance. The d skip is given as the mathematical expression of d skip is given as 2h into root over f muff by fc whole square minus 1. You all know that here h is nothing but the virtual height, f map is nothing but the maximum usable frequency, fc is nothing but the critical frequency. This is the expression used for the skip distance. The size of the skip distance depends upon the frequency of wave, the angle of incidence, and the degree of ionization present. The skip zone is the zone of silence between the point where the ground wave becomes too weak for reception and the point where the skywave is first returned to the earth. The size of skip zone depends on the extent of the ground wave coverage and the skip distance. When the ground wave coverage is great enough or the skip distance is short enough that no zone of silence occurs, there is no skip zone. So this is the skip distance means the transmitter to the ionosphere and ionosphere to the receiver. The first wave that will reach us from the region of the receiver. The distance is known as skip distance. The relationship between the maximum usable frequency and the skip distance is given by f map is equal to fc into secant theta is equal to 9 root max into secant theta. The value of f map is called maximum usable frequency and is less than 40 MHz and can be as low as 25 30 MHz in period of low solar activity. This above equation is called as secant law. The secant law is applicable for the flat earth and atmospheric layer. Critical angle, this is called as critical angle. Critical angle is nothing but the wave will not be reflected when theta greater than than theta c. Theta c is critical angle. The wave will be reflected when theta is less than theta c. So that the angle is known as critical angle. Above the critical angle the wave will not be reflected. Below the critical angle only the wave will be reflected from the ionospheric layer. The relationship between muff and skip distance. This is the diagram to determine the relationship between muff and the skip distance, and that relationship is given as f muff is equal to fcg into root over d square by 4h square plus 1. Where d is called as skip distance and h is called as virtual height. F is nothing but the critical frequency, f muff is nothing but the maximum usable frequency. From the diagram the cos theta is given by this expression, and it can be expressed like this, and we all know that f mop square is equal to fc square by cos theta I. In this expression, we substitute the value of cos theta I. Finally, we get the relationship between maximum usable frequency, critical frequency, and the virtual height and the skip distance. The relationship between maximum usable frequency and skip distance for the flat earth case and curved earth case. So this is for flat earth case and this is for curved earth case. Flat earth case means the transmitting antenna and the receiving antenna spaced very close. That means the distance between the transmitting antenna and receiving antenna is less than 1000 kilometers. Then we will consider the region as flat earth. When the distance between the transmitting antenna and receiving antenna is above the 1000 kilometers, we have to consider the radius of curvature of the earth. Nothing but it is called as curved surface. Thank you. This is about the sum of the frequency components in the ionosphere.